Alright, so let's move to the next part for the autoencoder, and we want to introduce another model. It's called Variational Autoencoder, or VAE for short. This part will be much more difficult or the challenge actually. So we make this part as optional for you. You just need to know the high-level ideas about Variational Autoencoder. So this is optional for you, and we also have an optional reading material prepared for you to understand materials which are covered in the lecture. So before we talk about this Variational Autoencoder, we also have another cutting page about the Bayes theorem. I assume some of you probably know the Bayesian equation, right? So we'll provide you with some basic information here. So the Bayesian equation is used to describe the calculation of some conditional probabilities. So given the probability following some distributions, right? Like we have PA given B. So this is something we know from our math course or from our statistics courses, right? So given the event B, what is the conditional probability of A event, right? So we denote this one as PA given B. This one equals to what? It equals to the joint probability of PAB, right? This true event happens at the same time divided by PB, right? By this single event probability. So this PAB also equals to what? This PAB also equals to PB given A times BA, right? It should be easy to understand, right? And how about this PB? This PB equals to the summation of all the A events. We calculate the product of PB given A times PA. So in this way, the PA given B will be calculated by PB given A, right? This will be very interesting. And it will also create some confusion sometimes, right? So in the bottom, we show you with a game. So let's assume we have 3 doors, and 2 doors will have a goat behind it. One will have a Tesla like Model X behind it. And I assume everyone wants to pick a door with a Tesla, right? And the one wants to get a goat, because nowadays if you get a goat, it will be useless, right? And you want to have a Tesla. It's our assumption you want to get a Tesla, right? And you can pick any door by yourself, and you can get the item behind the door by default. So let's assume the host knows what's behind the door, and given you random pick one door, say door number 1, right? And the host will open another door for you, say door number 3, which has a goat. And then the host will turn to you and ask you, do you want to switch to door number 2 or not? And what you will do. This is a very classic problem, right? About probability. So it also have something confusing actually. If based on the results, the host has opened the door number 3 already, then we only have 2 doors, right? One with a goat, one with a Tesla. The probability seems to be 1/2 and 1/2, right? It seems to be so, right? Because we know the door number 3 has a goat already by now. Then it seems it should be 1/2, 1/2, right? Then the real probability distribution behind these 2 doors will be what? If you insist to open door 1, the probability for you to get a Tesla will be 1/3. And if you follow his suggestion and switch to door number 2, the probability for you to get a Tesla will be 2/3 instead. And if you wonder, why it happens, why it is not a 1/2, 1/2, it is 1/3 and 2/3, why? Then you may search this multi-hole problem by yourself after class. Then there are so many articles or so many web pages providing you with answer. Why the probability will be like this, right? You can also write down the probability by the Bayesian equation as well. And it will be very interesting. So I leave this one as some toy homework for you, and you can check by yourself. And based on Bayesian equation, we can further introduce this Variational Autoencoder here. So the Variational Autoencoder is less similar to the previous autoencoder variants, because this one is not defined for deep learning. It's more like a Bayesian model, or it is more like a graphic model instead. So in the Variational Autoencoder, we have several key concepts. We assume we have a prior probability, P theta Z. And we also have the likelihood distribution of probability to be P theta X given Z. This Z, X are all the variables. This theta denoting the parameter of the distribution. And we assume we also have another probability which will be called posterior probability. It is p theta z given x. These two are both a conditional probability, right? And this one is a probability for z itself. And the problem we are studying here is how to generate a data instance xi, for example, that looks as real as possible. Here, if we assume we know the real parameters or the optimal parameters theta star for the distributions, right? If we assume so, then how can we do the generation? If we assume we know the theta, the optimal theta, then what we can do is actually to sample a random z, right, from the prior distribution p theta z, right? Then, if we want to generate this x, then we can utilize this likelihood function, right? So given this sample z, we can further generate a xi from a conditional distribution px given z, right? However, this one is based on the assumption that we know the optimal theta star, right? We can generate a data instance which looks real by two steps. First step is to sample z first, and then we can sample x, right? By two steps. However, in the real world, we don't know the optimal theta. We have to learn the theta from data instead, right? Then how can we obtain the optimal distribution parameter theta star? So the theta star can be obtained, by what? By a object function, right? We can define the theta star to be what? To be the arguments of the maximum function, right, on theta. Inside, we have the probability of all the instances that we have visited, and we time them together to compute the joint distribution probability, right? And we want to get a theta which can maximize the joint distribution probability as shown here, right? Because in the real world, we don't know this theta. We have to learn this theta from the distribution probabilities as shown here, right? And this object function can also be returned another way. We can by adding one more log function into this object function, because this log function is monotone, right? By adding it into this max function, it will not affect the solutions actually. So by adding the log function into this object function, we can get what? We can get the max theta log product on the joint distribution, right? It will also be equal to the argmax of the summation of all the log probability distributions, right? And we can rewrite the object function into this way. So it seems by solving this function, then we can find the optimal theta and we can address this problem, right? However, the main challenging part actually is how to define the px for this function. Because right now we know we have a pz function, right, a prior probability distribution. We know the likelihood, and based on them, we can also calculate the posterior distribution, right? And then how can we define this px, this distribution? So similar to the Bayesian equation we showed before, how do we define the PB, right? We define the PB as the summation of all A and then times PB given A times PA, right, together. It will be similar here. We can also sum all the potential Z, right? And then inside it, we can calculate the product between Px given Z times Pz and sum them together to define the Px distribution probability, right? However, this term will be very expensive to calculate because we have to enumerate all the potential z here, right? And then integrate them together. In other words, we have to enumerate all the potential z, which will be very costly because in the space we have infinity number of z's, and it will be very hard to calculate this px term by this equation, right? So then do we have any other ways to solve this problem? Do we have always enumerate all the potential z's so we can calculate this px distribution? Right? Someone probably say, can we just sample some z's? Right? Can we just sample some z's out? Then how can we sample these z's? Right? You may have this in mind. Can we just sample some z's out according to this distribution? And then we can utilize this z for calculating this term, and then we can further optimize the term to compute this theta star. So then what will be the problem? Because this one is a posterior probability distribution. According to this equation, if we want to calculate the pz given x, we also have to divide the PZX by PX, right? In other words, to define this posterior probability, we still have to calculate the PX, right? However, PX is very hard to calculate. In other words, this posterior probability will be very hard to define, right? Then do we have any other ways? This is a very challenging problem, right? So this is also the key part in the variational autoencoder model to be studied. So for the variational autoencoder model, the solution is to narrow down the manual space and to facilitate the fast search. So how do we address this problem? We address this problem by introducing a new approximation function, QZX. Before we mentioned that this PZX is very hard to calculate, but because if we need to define this term, we have to utilize this PX again, right? But this part is very hard to calculate. So we propose to introduce an approximation function QZX, and this one has another parameter phi as shown here for generating the z. And how can we ensure this QZX will work for us? We want to ensure this QZX will be an approximation of PZX. We want to ensure this equation will hold. Since this one also requires a computation of PX, right, it is very hard to calculate. But we just need to propose a new approximation function, QZX instead. This one can be approximation of this one, and it can be used to sample some z to help us narrow down the space and to facilitate the search process, right? So you can see how do we solve the problem for generate some data instances which looks as real as possible. We know this one will not work because this one requires we know the theta star in advance, right? Then the way we solve this problem actually is to optimize term. So instead of enumerate all the z's, we try to define one more distribution to help us narrow down the space to sample some z's, right? So given the x, we sample some z's, and use this z, we can further use it to define the px distribution, right? For optimizing the object function to learn the theta star. And then based on it, we can solve the problem, right? Then you can see why it is also called autoencoder model, right? Even though it is not a deep learning model actually. However, its main architecture it is very similar to the autoencoder. And you can see this approximation function QZX given x is like a probabilistic encoder actually. Given x, we try to get a z, right? As to the conditional probability px given z, it defines the probabilistic model like a decoder, right? You can see this, right? So with this, then we will be able to generate some data instances which looks real. However, here we only rely on the distributions. We don't use any deep learning anymore. Then by integrating them together, so before we say by optimizing this object function, we can obtain the optimal parameters for theta star, right? But here we do some changes to the object function besides this term. Right, we want to maximize. We also need to ensure the Q approximation probability is as similar to the true PZ given x, this probability instead. And we can quantify the distribution difference by this KL divergence function. Then we can define a loss function to be. Before we say that we want to maximize this term, then we can add 1 minus here, and we want to minimize this term instead. This is similar to what we cover. So this term is similar to what we show here, right? Here we maximize this term, and instead we minimize this minus instead. And we also minimize this KL divergence between the approximation distribution versus the true distribution, right? It will also equal to the negative estimation of all the z's sampled from the approximation distribution. Inside we have this log p theta x given z, right? And further we plus this KL divergence of this approximation distribution versus the true distribution on z. Because here we have a z sample from this one already, right? In this way, by minimizing this loss term, we will learn the theta star as well as phi star, which are the optimal parameters for the distribution of the p theta here, as well as the distribution of the q phi here. Also, we have a new challenge because here we have a sampling, right? Sampling is more like a stochastic process. Therefore, we cannot backpropagate the gradients anymore, right? And to further address this problem, inside the Variational Autoencoder, they have some tricks, like the Reparameterization trick, as shown in this page. So, given the x, we want to generate the probabilistic encoder, the QZX, right? Inside it, we can define the parameters phi involved by introducing a normal distribution. We assume this probability follows the normal distribution. It covers both the mean as well as STD, right? From it, we can run a sample one vector, and we quantify z to be sampled actually as the mu plus delta do the dot product with the sample vector, random vector, right? And we introduce two parameters. One is the mean, the mu, as well as STD. So according to the normal distribution, given the mean STD, we can generate a random vector. So in this way, we can redefine this z sampling process by following the normal distribution. So furthermore, based on this generated z, we can resample this x prime, and want to ensure that x prime looks as real as possible, right? So you can see why this architecture is also called the autoencoder, even though it's not based on deep learning anymore. It's a pure probabilistic model instead. So, but the general architecture is very similar to the autoencoder model. We have both the encoder and decoder, even though they are all based on probabilistic models instead. So this part is very complicated, I think, for you, right? And I added them to the slides just for your information. You don't need to know the details for now, and you can check it back when you need to use the Variational Autoencoder for your research or projects later afterwards. Alright, so that's it for this part, and we can do a very quick summary. In this part, we talk about what is autoencoder and what is the model architecture, and how to train the autoencoder model, what is the loss function for the autoencoder, right? And what can autoencoder do, and what are the advantages, and what are the potential applications of autoencoders. Then we also talk about some autoencoder varieties, right? And finally, we'll talk about this Variational Autoencoder. It's more like a probabilistic model instead, and why it is called autoencoder as well, right? And what is this Variational Autoencoder model architecture and learning process? This is the summary, and we also have some tasks for you to do after class. So please read the corresponding chapters in the textbook. And also optional, if you are interested in this Variational Autoencoder, you can refer to the section 2 of this article we provide in the schedule spreadsheet after class. If you think this part is too difficult for you, then you can ignore it, and it should be fine for now. Also for the project, it is also optional. If you are interested in how to implement autoencoder with PyTorch, we also provide you with a link. And if you are interested in the code implementations, you can also check it by yourself. Because in the project for this course, we don't have any models based on autoencoders actually. So you can check this example by yourself after class if you are interested. Okay, so that's for this section. Thank you a lot for your attention, and bye-bye.